Hello, my lovely geometry students. Today we are going to review content from section 2.5 of your textbook. It talks about postulates and paragraph proofs. So our goals out of this section are just to look at the basic geometry postulates that we covered in chapter 1 and use them to justify statements. So a postulate is a statement that is accepted true without proof. This is really the foundation of Euclidean geometry that we are studying this semester. We might do some other types of geometry later where these postulates aren't accepted without proof, and so because there's no proof of these statements, so they're just accepted. We will have numbers associated with the postulates that come from our textbook, but those numbers aren't universal. Every textbook will have different numbers. So when we use these statements, we want to use the conditional statements. We want to use them in their if-then form. We don't want to refer to it as the postulate number as much as we want to use the if-then form. So when we use these postulates and definitions, and all of our other arguments that we have in geometry, and we use them to prove a statement is true, then that statement then becomes a theorem. Okay, so we have postulates and theorems. We'll also look at axioms in later chapters. So here are some postulates. There's those numbers I was referring to. So your book calls this one postulate 2.1, but another geometry textbook might call that postulate 1 or postulate 2.8, depending on when they cover it. So don't refer to it by its postulate number. We're going to use the sentence. So these are pretty basic pieces of information that were covered in chapter 1, but now we're formally calling it a postulate. And these things that we're going to go through today are the foundations of the geometry that we will study this semester. So through any 2 points, there's one line. So we can connect 2 points and make a line. Through any 3 points, there's one plane. There's exactly one plane and exactly one line. And what that means is that if I tried to draw a second line or a second plane through those points, it would be identical to the first one. There's only one, it's exactly one, it's the same one. So 2 points make a line, 3 points make a plane. So then we can go back to say, well, then we know if we only need 2 points to make a line, then a line has to have at least 2 points on it. So if I drew that line through those points, we can see, though, that there are infinitely many points there, but we know it has to have a minimum of 2. Same kind of idea here with a plane. When we have a plane, we know that we have to have a minimum of 3 points to make a plane. Scoot that plane over so that you can see they're all 3 in the plane. So we need a minimum of 3 points to create a plane. Now, with those 3 points on a plane, we could draw 2 unique lines. So if I were to draw a line on that plane, we would see then that that whole line has to be in the plane because the 2 points that made it are in the plane. And that's what postulate 2.5 says. So because we have line DF is in that plane, line point G that is on DF is also in that plane. So any point on line DF would be in the plane that DF is in. So postulate 2.6 and 2.7 talk about intersections. Again, this is something that we studied in chapter 1, but we're just formally stating it as a postulate. So if 2 lines intersect, we expect the intersection of those 2 lines to be 1 point. So there's that 1 point where they intersect. And if we have here 2 planes that intersect, their intersection is a line. So in this picture here, I have plane R and plane P, and they intersect in this line here, HI. So keep in mind that they intersect in that whole line. So any point that is on that line is in plane R and in plane P at the same time. So it makes up this set of infinitely many points that are in both planes. So we call that line HI. So we can use these postulates to justify whether statements are sometimes true, always true, or never true. So when we explain our reasoning for these, we have some expectations. If we say that something is always or never true, we need to be able to justify it with a postulate, a theorem, a definition, etc. We have to use deductive reasoning to say, why is that always or never true? Those are a little easier because when we have a sometimes, we need to provide two examples. An example that says it is true and an example that shows when it's not true. So when you're doing an always or never, you need the reason why it's always true or the reason why it's never true. If it's sometimes, you need to show me a case where it is sometimes true and a case where it's sometimes false. Okay, so we have to justify why that's the correct answer. So here's the first one. If a plane T contains line EF and line EF contains point G, then T contains point G. So we can say that this is a statement that is always true because of postulate, one of our postulates that said that. So let's go back and see which postulate was that. What was the if-then statement? Right here, it was postulate 2.5. It says that if 2 points lie in a plane, then the entire line containing those points lies in a plane. So that would justify that statement. So we can write that, or I will copy it. Oops, went too far. So then what we're doing is we are saying it's always true, and then our justification, why is it always true, we're using our postulate. Okay, so part of your assignment that you're going to have from this section, one of the things you're going to have to do is you're going to have to use those postulates to justify your reasoning. So this is a situation where we're going to have to start to remember all the different postulates and rules and definitions that we're going to be exposed to this semester. Here's another example. Line GH contains 3 non-collinear points. Well, that statement is never true because by definition, non-collinear means that they're not on the same line. So by definition, oh, I think I misspelled that word. Means that 2 points are not on the same line. Okay, so I'm justifying my reasoning with a definition of what it means to be non-collinear. So I gave you an example of where I used a postulate to justify. Here I used the definition of non-collinear. Remember, when we're talking about deductive reasoning, postulates, theorems, definitions, facts, those are the things that I can use to justify my statements. Another look at what we did first section or first chapter, we had the midpoint formula where we looked at coordinates in the coordinate plane and found the midpoint between 2 points. Well, this is a little bit more of a geometric approach to that same concept. This is called the midpoint theorem. So the midpoint theorem, and we can prove this, it's been proven multiple times, but the midpoint theorem says for any segment, if you know that a point is the midpoint, that it divides it into 2 congruent segments. So if M is the midpoint of segment AB, then we know that those 2 new segments that are made by that midpoint are congruent. So segment AM is congruent to segment MB. Just for a review of notation, don't forget when we put those tick marks, right, on line segments, that is a visual way of showing that they are congruent. Okay? So notice that there are no numbers here. And that's the beauty of proving things, and in geometry we're going to do a lot without numbers. We're just talking in general for any segment. I don't need to know how long the segment is to say that there is a midpoint that would divide it into 2 congruent halves. So this is something that we're going to transition away from specific numeric examples. We're going to start looking at more general concepts. where we're focusing in on the idea that the midpoint divides it into two congruent halves. Even though I don't know the length of the segment, I know that the midpoint's still going to do that. So as we are beginning to look at all these postulates and all the theorems that we're going to have this semester, we're going to start to link those things together to create a logical argument. And that's what the heart of a proof is, okay? Where we're going to make a logical statement, and then we have to justify that statement. And then from that statement, we're going to make a new statement. And what we'll end up doing is we'll end up proving general cases of things. So every single argument that you make in a proof, though, has to be justified using that deductive reasoning that we've been talking about. So we're using the rules, the postulates, the properties, the theorems, the definitions, those things to create and justify our logical argument. There are four main types of proofs that we will look at this semester. The first one is a flow proof. A flow proof works like a flow chart where you have multiple statements coming together to create a new idea or a new statement that we're justifying with those rules and postulates. Paragraph proofs are exactly what they sound like. It's a paragraph of complete sentences. I don't really like to grade those a whole lot, so we won't do a whole lot of those. I'll be honest. A proof by contradiction is generally written as a paragraph proof, but it is unique because it begins by assuming that something is not true. So instead of starting with what you want to prove to be true, you start that what you want to prove to be true is false. And then you find that there's a contradiction in there. And we'll do a couple of those. They're actually much more common as you begin to dive into more advanced mathematics. You'll see a lot of proof by contradiction. The last type, the one that we're going to focus on the most, is a two-column proof. Two-column proofs create this statement and reasons T-chart, where we make logical statements over here in the statements column on the left, and then we put the reason that justifies that statement, what postulate, theorem, rule, definition, that justifies the corresponding statement on the left, all the way down. And so we're creating this chain link of ideas. Okay. We'll focus in on doing two-column proofs here in geometry, but we will take a look at some of the other kinds as we go forward. So that's it. That's the majority of the information from 2.5 of your textbook. If you would like to go back and copy down those postulates into your notes, that would not be a bad idea, keeping in mind that you're going to be expected to know these things, and you're going to be expected to use them to justify your statements. So if you need to go back, pause the video, and jot those down. They're straight out of your book. You can do that as well. All right, and then we'll be using those in the homework to do the true, always true, sometimes true, never true stuff. All right, great job, guys.